Hey everyone! The goal in this video is to introduce a few variance reduction techniques in Monte Carlo methods and how they reduce the variance when estimating pi using the circle in a square problem. So the motivation here is that the error in Monte Carlo techniques decreases as sigma over square root of n, where sigma is the standard deviation of the underlying samples and n is the number of samples. This means we can just take more samples to reduce the error bars, but the error reduces painfully slow due to the square root. So the more strategic thing to do is to focus on the sigma and try to reduce its value such that we don't need as many samples to obtain the desired error bars. Before introducing the variance reduction techniques, let me outline the problem setup. So we're trying to estimate the value of pi by inscribing a circle in a square and uniformly throwing a bunch of random darts. The probability of the dart hitting inside the circle or outside of it is going to help us compute pi. Note that we can simply focus on one quadrant because of symmetry. Then the ratio of the circle's area to the square's area is going to be pi over 4. In other words, the probability of the dart hitting the circle is pi over 4. So an estimator for pi is going to be 4 times the indicator variable I. This indicator is equal to 1 if the dart hits inside the circle, namely if x squared plus y squared is equal to or less than 1, and it's equal to 0 if it hits outside. As we said, the probability of it hitting inside is pi over 4, and the probability of it hitting outside is 1 minus pi over 4. We will call this estimator f, which is again 4 times I. Now the simplest way to sample is to use uniform sampling. Here we draw the x-coordinate of the dart from a uniform distribution between 0 and 1. And we do the same thing for y-coordinate. Then if x squared plus y squared is equal to or less than 1, namely if the dart is inside, then our sample value is equal to 4 and 0 otherwise. If you imagine the sample values we get as we run our Monte Carlo, it's going to look something like this. Here we will have the 4 line, the pi line, and the 0 line. In this case, we will see a bunch of 4s and 0s in our sample set. In other words, we're essentially trying to arrive at the correct value of pi by taking the appropriate averages of multiple 4s and 0s. As you can imagine, this is pretty inefficient, and the jump between our samples is huge, which means that we have a high variance. In fact, if you do the simulation of this, you will see that the variance, which is sigma squared, is close to 2.7. We can convince ourselves that this is the right value for the variance because in the case of uniform sampling, we know the exact value for it. Note that our indicator variable is a Bernoulli variable, namely it's 1 with probability pi over 4 and 0 with probability 1 minus pi over 4. We also know that the variance of a Bernoulli variable is equal to p times q. So the variance of our estimator f can be obtained exactly as the following. So when writing the code for variance reduction techniques, it's a good idea to first implement the uniform sampling and to make sure that its variance is close to this value. Now we can start talking about some variance reduction techniques. Let's first discuss the importance sampling approach. To explain it, let's assume that we're interested in the expectation value of some function hx. Also, let's say this function hx is very localized. In this case, if we use a simple uniform sampling, most of the estimator values we get are going to be close to 0, and we're mostly going to miss this peak. So then the idea is to introduce another distribution, let's call that gx, which ideally should be close to hx. Then we're going to multiply and divide the integral by gx. Now we get a modified estimator where this gx acts as a weight, and the samples are drawn from gx instead of uniform sampling. By the way, if you want to draw from any custom distribution gx, you can use the inverse transform sampling. In this approach, we have our desired distribution gx, and we also calculate its cumulative distribution function. Then we draw from a uniform distribution and then find the inverse value of the CDF, which gives us the desired sample from Gx. Intuitively, we can convince ourselves that this is going to work because if we imagine a localized function, the CDF is going to have a sharp rise around the peak. Then when we draw U from a uniform distribution, most of the samples are going to end up near the peak as expected due to the flat region in the CDF. Coming back to our problem, we are going to use an exponential function gx as such. We will also use the same function for gy. This is just a guess function and most likely not the most optimal one. Here lambda is a free parameter which is set to 0.6 here, and the term in front of the exponential is needed for normalization. Overall, the weight function is gxy equal to gx multiplied by gy. So the expectation value of f using the uniform samples is equal to the expectation value of weighted f with samples from gxy. In other words, this is an unbiased estimator because the mean is the same, but the variance is now expected to drop. Actually, in this specific case, the variance does not drop significantly using the importance sampling. The reason is that the estimator takes a value of 4 until distance r and then it suddenly drops to 0. But our gxy has a qualitatively different shape. Nevertheless, we obtain some variance reduction where the variance drops from about 2.7 to about 2.16. Also, let's again visualize how the samples will look like. First, if we have a dart outside the circle, the sample value is still 0 because it's 0 multiplied by a weight. But if we have a dart inside the circle, it's no longer a constant 4. In fact, it now depends on where it lands since the weight gxy depends on x and y. We can actually get a sample values above and below the pi value as opposed to the uniform case. And again, we can intuitively see why this should be helpful with variance, since we're no longer trying to estimate pi with just 4s and 0s, but we're using sample values that mostly fluctuate around pi. Now let's move on to the next approach, which is the control variate technique. Again, we're trying to find the expected value of the estimator f, but what if we exactly knew the expected value of another estimator g? If this estimator g is somehow correlated to the estimator f, we can indeed exploit this information to reduce the variance of f. To do this, we make a new estimator f prime, which is equal to f plus c multiplied by capital G minus g. Here capital G is the known expected value of g, and c is an unknown scaling factor. And the main idea in the control variate technique is to make a correction on the usual f, using the error on the estimator g. Now we look at the variance of f prime. As a reminder, let's quickly derive the general expression for variance of this form. This gives us this expression for variance of f prime in terms of the unknown coefficient c. Since we're trying to minimize the variance, we can take the derivative of variance f prime with respect to c and equate that to 0 to find the c coefficient. The resulting value for c is covariance fg divided by variance of g. Interestingly, this is also the slope we obtain from linear regression for f versus g. Now let's plug in c back into our equation for variance f prime. We will multiply and divide this term with variance f to cast it into a form with correlation coefficient rho. At the end, we get an expression with variance f and rho fg. This expression tells us that the more correlated g is to f, the more variance reduction we see in the estimator f prime. But coming back to our problem, how should we choose the form for g? Well, we need to think about the structure of our problem and the form of f. We know that I is 1 if x squared plus y squared is equal to or smaller than 1 and 0 otherwise. This gives us a suggestion that we could use g is equal to x squared plus y squared. Also, we can easily take the expected value integral for this function, and the result is 2 over 3. Now we can finally build the final form for our new estimator f prime by plugging in c and the capital G. Again, this term can be seen as a correction, and the expected value of this term is 0, and therefore this is an unbiased estimator. Expected value of f is calculated as usual. G is equal to x squared plus y squared, and the coefficient can be calculated once all the samples are accumulated. The new variance with this approach is about 1.15, which is a significant drop from the original 2.7. Also, if we visualize the samples, we see that the samples fluctuate around the value of pi, and we don't get zero values in general due to the correction term. The control variate technique is useful if evaluating G is cheap, its expected value is known, and also the correlation is close to 1. Next, let's move on to the antithetic variate technique. Here the idea is simple but powerful. Imagine if we have two random variables x and y. The variance of the sum is again given by variance x plus variance y plus 2 times covariance xy. Again, if we can make the covariance term, namely the correlation between x and y, negative, it will reduce the variance. So we create a new estimator f prime, which is f1 plus f2 divided by 2, where we try to make f1 and f2 negatively correlated. In this problem, we have f1 sampled as usual, x, y, but we sample f2 as 1 minus x and 1 minus y. But why does this help? Well, if you imagine a dart that landed on the inside, the antithetic pair is likely to land on the outside, or vice versa. In other words, if we look at our samples, you will see that the value we get are fluctuating between 2 and 4. That's an improvement over fluctuating between 0 and 4. In fact, the variance from this is about 0.98. As you can see, it's a pretty simple modification to how we sample, but the variance reduction is surprisingly significant. Finally, I want to mention that you can mix and match different variance reduction techniques. For example, let's consider control variate technique combined with antithetic variate technique. Here we start with the usual antithetic approach, where we draw x1, y1 for f1 and x2, y2 for f2, where x2 is equal to 1 minus x1 and y2 is equal to 1 minus y1. Then we form the f pair, which is equal to f1 plus f2 divided by 2. However, we further modify the fp to be corrected by the control variate technique using g pair. Here, gp is equal to g1 plus g2 over 2, so the expected value is still 2 over 3. And g1 is equal to x1 squared plus y1 squared, and g2 is equal to x2 squared plus y2 squared. Using this approach, we can slightly reduce the variance even further, down to about 0.77. A link is provided to the code of these methods in the description below. But as a summary, these are the variances of different techniques we have covered in this video. Thanks for watching.